Hello everyone, here we'll be discussing triple integrals, which is basically an extension of what we discussed with double integrals. We're now going a step further. Now remember, double integrals represented the area, well, not area, but volume under a surface, kind of like how a single integral is the area under the curve. So what does a triple integral represent? Well, it actually represents a fourth dimensional version, you can say, of volume, which is called hypervolume. Now it's kind of hard to describe though. So imagine we have some object in three-dimensional space. Let's just have our dimensions oriented like usual. Now let's call this object usually is called E. So some three-dimensional object called, let's say, E, something like that. Now E, this three-dimensional solid, believe it or not, is actually a shadow of a fourth-dimensional object. Kind of like how this here is the projection of this three-dimensional object onto the two-dimensional xy plane, or you can find a similar shadow in the xz dimension or in the yz plane as well. But in 4 dimensions, it's really hard to visualize what that looks like, but at least we can say that its projection into 3 dimensions would be a three-dimensional solid, which again sounds kind of funny, but think of how it works from 3 to 2, and then similarly from 2 to 1. So here we have this 2-dimensional figure that has a 1-dimensional shadow. Just like this 3-dimensional figure has a 2-dimensional shadow, a 4-dimensional figure will have a 3-dimensional shadow, which is just an object, which looks weird. So it's like a solid basically. So now there are a few things we can say. First off, this is the definition for Riemann sums, which we're not going to talk about too much. I'll just show you it. That's basically it. Now Fubini does have a theorem that is, well, a triple integral version of what we saw with double integrals, which basically says that if f is continuous on the rectangular box, which is you can think of as a to b, c to d, and r to s box. So remember how that works. This is in the x direction, y direction, and z direction. So we have these intervals on x, y, and z axes, and if we cross those, we get some three-dimensional box. Then the triple integral over b of f of x, y, z dv is just this. It's literally an iterated integral where your x limits are a to b, y limits are c to d, and your z limits are r to s. And you can actually go in any order. So if you want to do dx first, then of course you have to set it up that way. And then otherwise, if you want to do dy first, then you're free to do that as well. Now we have an example here where we'll basically be using Fubini's theorem. And beyond this, we're going to have to take a look at a few different types of scenarios, kind of like we had with double integrals. There were 2 types. There are actually 2 types as well over general regions that aren't just rectangular boxes, which I think we'll do maybe 1 or 2 examples of, and then finally we'll move on to an application of triple integrals that will actually be more intuitive, whereas 4-dimensional hypervolumes is not very intuitive. So right now we're just going to find this number, and the number represents the 4th dimensional measure of this 4th dimensional object. Again, it's hard to graph. You can't even really graph it, but you can try to, but it gets really, really hard to visualize. So with that said, let's just continue here using Fubini. So I want to say that this triple integral is the triple iterated integral of x, y, z squared. And let's do it just in order, dx, dy, dz. It's possible that the ordering could be switched around, like I said, and depending on what you want to accomplish. But since we know the limits and they're all constants in this case, notice the x limits are just 0 to 1, the y limits are just negative 1 to 2, and the z limits are just 0 to 3 in this case. Then we can just proceed from the inside outward. So we'll do this guy first. Then after doing that one, we'll take care of this integral. And then finally we'll do the dz integral. So that's really all we're doing, just kind of like what we saw for double integrals, only 1 step further, like I said. So it's not too bad, but let's see if we can handle this. So the antiderivative of this with respect to x, yz squared is a constant, remember? So it's going to be x squared over 2, or if you like, 1/2 x squared. And in fact, you know what? Let me do the side work here. So it's 1/2 x squared yz squared. And we're going to evaluate this between the limits 0 to 1. When you plug in 0, x squared gives you 0 squared, which is 0, so that 0 is out. When you plug in 1, x squared is just 1. So in reality, all we really get is 1/2 yz squared. Perfect. So the red integral is taken care of, and now we have this integral dy between -1 and 2, and then our dz integral after that, which is from 0 to 3. So now the integral with respect to y now, the antiderivative of y is 1/2 y squared, so this is going to be 1/4. Before we get to that though, let's do the side work kind of like we saw here. So antiderivative of 1/2 y is 1/4 y squared. Z squared comes down to 3 because it's a constant multiple like we saw earlier in the eyes of y anyways. Evaluate between -1 and 2. When you plug in 2, 2 squared becomes 4 and those cancel, so this just gives a z squared for that expression. When you plug -1 squared is just 1 times 1/4 is 1/4, so it's minus 1/4 is z squared. Perfect. Now of course 1 minus 1/4 is 3/4, so really this is 3/4 z squared. Now we have our limits 0 to 3 dz, and now we can take the antiderivative with respect to z, finally. And that's going to give us 1/3 z cubed, but notice 1/3 and this 3 cancel. So we're going to get 1/4 z to the third, evaluated between 0 and 3. When you plug in 0, it's all 0. When you plug in 3, you get 3 to the third, which is 27/4. So this value here represents the fourth dimensional hypervolume of this fourth dimensional object. So yeah, again, a little crazy, but that's what it represents. So now we're going to move on and take a look at a few different types of regions that are not rectangular boxes, and then we'll move on from there. All right, so we have these 3 types of regions. These are kind of general regions. There are regions that are not of this type, but usually what we'll be seeing are of this type. This is the way we can categorize it. Now, just to explain what this type really tries to do is it tries to give us some type of cylinder. So if you imagine a cylinder, you have a circle on top, a circle on the bottom, and you have a straight line. Now, our cylinder isn't actually going to be like this, where each top is not circular, and we're not even required for them to be really the same as far as shape. So for instance, the top could be squiggly like this, and the bottom could be some other type of squiggly, or rounded in one part and squiggly in the other, for instance. But of course, this is in the background, it's happening behind. The point is we're connecting with these kind of straight lines. So whether that is orientated like this, like that, or like this, these are the 3 different types. So here we'd have a dimension, well, not a dimension, we'd have a projection, I guess you can say, or a shadow with this orientation in the xy plane. So that would be type 1. If your projection is on the yz plane, then it's type 2, and if it's in the xz plane, then that's type 3. So that's really what this is. And what's really nice is that with this being said, all we really need to do is take the antiderivative, or I guess integral, you can say, between those 2 functions in that kind of missing direction. So in this case, the direction or dimension that's missing in our xy plane is the z dimension. So we can take this integral with respect to z over these 2 functions. Now these functions are really what are kind of creating these curves. So you'll have a top function on top and the bottom function on the bottom. So the top function we generally call u2, and the bottom function we call u1. Now in practice, we won't really be looking at this too much as far as which one's type 1, which one's type 2, and so on. We'll see some examples. I think I want to do at least 2 examples. But you'll see after a while that the types are kind of the same. It's just literally a change in variables. And you know, the orientation may be kind of weird to get used to at first, but the point is you just handle the integral in 1, and then this boils down to now a 2 or double integral, like we saw from the previous sections. Now, with that being said, the 2-dimensional region, in this case D, the projection into the xy plane, may be type 1 or type 2 in the context of a 2-dimensional region, not in this context. So that's where things get a little weird. So let's take a look at an example right now and see how crazy it gets. Okay, so here for this example, we're going to evaluate this triple integral over E of z dv, where E is the solid tetrahedron bounded by these 4 planes, x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. So to try to figure out what that looks like, let's graph a little bit. So in 3-dimensional space, we have these planes, well, these axes, I guess. So x equals 0 is really just the yz plane. In fact, if you think about it, x equals 0, y equals 0, and z equals 0 are just kind of telling us that we're in this octant, which I don't think I've actually spoken of, but an octant is just kind of what you'd say for a quadrant, but in 3 dimensions. So there's actually 8 of them instead of 4 of them, which is what we call an octant and not quadrant anymore. But anyways, let's see. So x plus y plus z equals 1, that's a plane because it's linear. And actually, if you let x, y, and z are each be 0, 1 at a time, or I guess 2 at a time. So if x and y are 0, z is 1. So let's say that's 1. That's 1, and that's 1, let's say. So when y and z are 0, z is 1. When y and z are 0, x is 1. And when x and z are 0, y is 1. So what we end up getting is this. And we end up getting this kind of slanted triangle piece. And if you connect to the origin 0, 0, 0, this is the tetrahedron that we're talking about. So if you don't know what a tetrahedron is, a tetrahedron is kind of, imagine like a triangle. Well, imagine a pyramid with a triangular base. So this is an example of a tetrahedron. And that's exactly the shape we have here. So notice we have this lower triangular base, and we have this triangle up here, and these other triangles behind, really. So we have these 4 faces that are each a triangle. Perfect. So we want this, so that's E. And now, first off, what type is it? Well, honestly, it can be whatever type you want, because if you kind of think about it, there's a projection in the xy plane, in the xz plane, or in the yz plane. But I'm going to treat it as a type 1, in which case I need to call it out. So I'm going to say E is such that we have these this point x, y, z, such that x, y is in some domain D, and z is actually in between. Well, let's see. Yeah, so z isn't actually too hard to determine. The lowest z can be is on the xy plane, which is when z is equal to 0. So the smallest z can be a 0. The largest z can be is actually touching this slanted triangular part, which is just this plane itself. And if you solve for z here, notice z is just equal to 1 minus x minus y. Perfect. The only issue now is that what is d? Well, now we have to interpret that by looking at the shadow. So if we kind of draw an xy plane, let's say, and again, this would be in the first quadrant like this was in the first octant, this line right here represents, let's say, this line right here. Let me just look at this line segment only. Now, notice this is going from y equals 1 to x equals 1 like that. Now, this line is actually the line y equals 1 minus x, which is actually not too hard to see. Basically, it has a y-intercept of 1 and a slope of negative 1 over 1 because it goes down 1 over 1. So by y equals mx plus b, it's y equals negative 1 plus 1, or 1 minus x if you like. So with that being said, D is just the set of all points x comma y, where x is in between 0 and 1, because this is our domain here. So x is in between 0 and 1, but y is actually in between, well, 0 and 1 minus x. So I know it's a little hard to kind of figure out as far as how I did it here. I mean, it's not super intuitive, but after a little bit, you get a feel for it. And really, it's just looking at what shadow you like. And I like the XY shadow. So that means Z is going to be in between these two pieces here. Again, the XY plane, which is 0, Z equals 0. And this plane, which is X plus Y plus Z equals 1, which we can solve for Z like we did here. Good. Now, to actually solve the triple integral, though, well, I'm actually just going to straight up turn this into an iterated integral, if we can. So the iterated integral I'm going to turn this into is getting rid of z first. So it'll be our integrand, which is just z, notice, dz. The bounds for z are 0 to 1 minus x minus y. Then, here we want to get rid of y because the constants are on x, so I want to get rid of y here. So I'm going to do dy now in between our bounds 0 and 1 minus x. And then finally we're going to do dx, which is in between these bounds 0 and 1. Remember, whatever your constant bounds are, that's going to be your last integral. So that right there tells me that it must be in this order, the way we were setting it up anyways. Now the antiderivative of z with respect to z is just 1/2 z squared, like that. If we evaluate it between 0 and 1 minus x minus y, plugging in 0 makes a 0. Plugging in this top guy makes a 1/2 times that guy quantity squared. that's going to be a little weird. I think we have to expand this out, and there's really no choice here. And I've kind of run out of space. So if you don't mind, I'm going to erase practically everything, shift this up, and we'll continue. Right, so I've gone ahead and erased a few things and shifted this up where we left off. Now, I mentioned that we could possibly expand this, but actually there's a better way of doing it. Notice that we're taking the integral with respect to y, and 1 minus x is then a constant in regards to y. In other words, you can think of this as, let's say, 5 minus y all squared, just as an example. Now, the antiderivative of this is going to be, so imagine integral dy, is going to be 1/3 the inside to the third power, but then of course you have to multiply by the reciprocal of the derivative of the inside only when the derivative of the inside is a constant by chain rule, this particular instance of chain rule. And it's a -1 in this case because derivative of the inside is -1. Notice if you take the derivative of this, the 3 comes down by power rule, cancels this 1/3, so it gives us this to the second. And by chain rule, derivative of the inside is -1, which cancels the negative. So this indeed is the actual antiderivative of this expression, with the exception of that 1/2. Now, speaking of which, 1/2 and -1/3, they're both constant multiples, so we can actually pull that outside of the integral. So I'm going to do that. So if we pull the -1/3 and 1/2 multiplied together, that's -1/6 outside of the integral from 0 to 1 now of something dx. Now the antiderivative of this is not 5 minus y, but it's 1 minus x minus y. And we said that the antiderivative would be 1/3, -1/3 times that to the third, but the -1/3 we already pulled out. So I'm just going to look at this expression here and evaluate between our limits, 0 and 1 minus x. There's a lot of moving parts and I'm kind of going a little out of order. But notice when you plug in 0, you don't actually get 0. When you plug in 0 for y, you just get 1 minus x cubed. But notice, when we plug in, so that's the second part of the evaluation, when we plug in 1 minus x, we actually get 1 minus x minus the quantity 1 minus x. So think of it like this, 1 minus x minus the quantity 1 minus x, all cubed. Now, remember, this is 1 minus x minus itself, basically, so this first part actually zeroes out. So that zeroes out, and 0 cubed is 0, so that becomes unaffected, basically. Well, kind of, but we still have to do minus the evaluation of 0, so it's going to be this, actually. Which is really nice, because notice we can pull the negative out here, and that cancels this double negative now. Well, it makes a double negative, which cancels out the negative. So we're just left with this. Now this we can handle in a very similar way that we handle the antiderivative of 1 minus x minus y all squared. Antiderivative of 1 minus x to the third is 1/4, 1 minus x to the fourth, 1 minus x to the fourth. But then by chain rule, you have to divide by -1, which just accounts for a negative. Perfect. So now this -1/4 we can pull out with this 1/6, and that gives us -1/24, 1 minus x to the fourth. And now we have to evaluate this guy in between the limits 0 and 1. Now when you plug in 1, that zeroes out, because you get 1 minus 1, which is 0. So we get -1/24 times the first evaluation, which is 0, minus the second evaluation. Here is going to be 1 to the fourth, which is 1. So notice this is just -1 times negative. This is actually positive 24, 1/24. Nice. So it was a bit to do. The setup was, I think, the most complicated part. After that, the integration wasn't actually that bad. And remember that it's iterated integration, just like I've shown here. So I hope it was okay to keep up with. And now we're going to take a look at another type of example then. Okay, so now for this next example, we're asked to evaluate this triple integral over this region E of the square root of x squared plus c squared dv, where E is the region bounded by the paraboloid y equals x squared plus z squared, and the plane y equals 4. So just to give you an idea of what this looks like visually, we can graph, of course, in 3 space. And the image we get somewhat looks like this circular bowl that opens out like this, stemming from the origin. Now, where it stops is actually at y equals 4. So imagine drawing a line here, y equals 4. We end up getting this plane. And that circular cut is just the end of that bowl shape. Now, the bowl shape really is a paraboloid, and a paraboloid is essentially what you get if you imagine rotating a parabola around the y-axis into the third dimension like that. So in fact, what you can do actually is if you want to treat this as a type 1 integral, then its projection onto the xy axis actually would look something like this. So onto the xy plane, I meant to say, you end up getting this parabola. Let me draw that a little more centered. Looks a little better maybe. Y, x. And we have this line y equals 4. Now this is the projection of this three-dimensional object E onto the xy plane, and we end up getting this being our domain in 2 dimensions. So if we were to set it up like this, then we want to integrate with respect to z first to lose the z dimension to project onto the xy plane. And z at most can be the top part of this paraboloid, and then at least, so the lowest point will be the bottom part of the paraboloid. Now the paraboloid has this equation, and if you solve for z here to get the limits for z, you end up getting that z squared is equal to y minus x squared. And then if you square root, you get z is plus or minus the square root of 1 minus z squared, or x squared. Yeah. Which makes perfect sense because the positive represents the highest point, where the negative represents the lowest. So we end up getting something like this maybe. Okay. Now the integrand is still x squared plus z squared inside that radical. But now we're going to tackle dz first, then integrate with respect to, well, now when it comes to this this region D here for the double integral now, notice this is type 1. X is in between what and what? Well, x will have to be negative 2 and 2, so that when you plug it into the parabola y equals x squared, squaring negative 2 and positive 2 gives you a y value of 4 each. So our x will be our last integral, which is from negative 2 to 2. And then for the y's, the largest y can be in this region is 4, and the lowest it can be is hitting the parabola y equals x squared. So we're going to do dy first, and then dx. Now, I'm not actually going to integrate this. As it turns out, this is extremely hard to integrate the first integral with respect to z, because this is a number plus z squared, because remember x is constant in the eyes of z, inside a radical. And you can do that by trig integrals, but it gets pretty hairy. To be quite honest, this integral in general, this triple integral, is actually very, very, very difficult to do. I'll still show you somewhat how to do it, but this is not the correct setup I want to keep in mind. So now, here I just showed you using the type 1 setting, but it's not working because this is hard to do. Now, why is it hard to integrate is because it's a number plus the variable squared inside the radical. But notice if we were to rearrange this in some way, so we had dx first, we'd have the same problem because this is symmetric about x and z. But if we integrate it with respect to y first, the integral of this expression here with respect to y is just itself times y, because it itself is a constant in the eyes of y. So I hope that makes sense. But now with that being said, let's get rid of these limits. Let's see if we can rearrange these in that particular order, where we do y first. Now if we were to integrate with respect to y first, that means we're losing the y dimension now, and we're going to project this onto the xz plane. So let me try to draw that here. In fact, let me move the projection drawing over here, let's say. So onto the xz plane, let's imagine this is the x-axis and that's the z-axis, just like that, but imagine just flattened out towards the xz plane. The image you get is actually this circle. This is the shadow of that paraboloid. Now the equation of this circle, well, first off, the radius of the circle is going to be 2. And I know that because what we said earlier, that x is negative 2 and 2 and y is equal to 4. So that's just kind of, in fact, let me show in a different color here. So we can see when x is equal to 2, for instance, that projects exactly to this part of the paraboloid. Perfect. And we know the equation of a circle with radius 2 is the squares of the variables, x squared plus z squared in this case, equals the radius squared, which is 2 squared, so that's 4. Good. So this is the region for our double integral. Now as far as the limits for y, what is the largest y can be and what's the smallest y can be? Well, the largest y can be here is y equals 4. And the lower bound of y at any particular cross-section of this will actually be the paraboloid itself. So the paraboloid, luckily, is in terms of y already. Well, y is isolated, I should say. So y is going to be equal to x squared plus z squared, and that's kind of the lower point of this. It's hard to kind of draw that, but I'll draw it here a little bit just to show you. So I'm going to reorientate this so that y is on top, and now we have xz like this, let's say, just to kind of reorientate so we can figure out what's going on. We have this paraboloid shape, and what we can say is that if you take any particular line here, the largest y can be here is y is equal to 4, but the lowest it can be is actually on the plane, or not plane, but on the surface of this equation, which is y is equal to x squared plus z squared. So it's kind of like the floor in this sense. So depending where you're at, basically, the lowest point would be on the paraboloid itself. So I hope that part's not too confusing. But now this part is actually okay to take the antiderivative of. But now here, when it comes to this, we can do, let's say, x last, negative 2 to 2 still, and then dz would be in the middle. The largest z can be is when, well, it's kind of like we did for y in the previous one. I guess it was z in the previous one for this. Here we're going to solve for z, we'll get a radical. This is going to be square root of 4 minus x squared, but it's plus or minus if you solve for a z here. So you can try that on your own, but you get negative radical. That's going to be 4 minus x squared for the lower limit, and then positive radical 4 minus x squared for the upper limit. Okay, so I know it's a lot to look at, but anyways, let's focus on the first integral here. This guy. So now let me erase a lot of this. I'm going to erase all of it actually below here. So now the antiderivative of this expression, again with respect to y, is just itself times y. So if you want to think of it as y times that radical, that's what the antiderivative is with respect to y. And now we have to evaluate between these y limits, 4 and x squared plus z squared. Now in doing this, it's actually not too hard to see that when you plug in 4 to be this minus 4 to be that, y to be this minus y to be that, this is a z squared, sorry. What you really end up getting is the following. You get 4 minus x squared minus z squared all times the square root of x squared plus z squared. Now I'll allow you to figure out the details of that on your own, but again, it's not too hard to see. When you plug in 4, you get 4 times this radical. When you plug in y to be this, you get that times the radical. But when you subtract, you get 4 minus this quantity all times that radical. If you distribute the negative into that quantity, you get this here. But now we still have these two to take care of. And now let me lower this, in fact, just so I can squeeze that in there. So what do we have? We have 4 minus x squared minus z squared times this radical of x squared plus z squared. Now this is where I'm going to possibly go a little bit over our heads for a moment, because this still is a super difficult double integral to do. But at least we're now down to double integrals opposed to that triple integral. And I'll say right now, the hardest part of any of these examples is the setup. But in any event, let's see if we can handle this. So here's what I'm going to do. If we were to try to do this by normal Chapter 7 methods, we would actually need trig integrals. Or not trig integrals, but trig substitution actually. And the trig substitution is pretty wild. And you'll end up getting like secant to the fifths, and it's a mess. So I'm not going to do that. It's doable, but it just takes too long, and it's a lot to look at. Instead, I'm going to show you something that, again, you may or may not have seen before. And this is polar, we're going to discuss this as a polar integral. Now to do that, and why that is the case, is because I see this x squared plus z squared, and I know that this right here, I erased it earlier, but on the xz plane, this is just the circle of radius 2. Perfect. So the double integral can actually change quite a bit, but we have to keep in mind that we have this equation, x squared plus z squared is equal to 4. Now, we're going to integrate over this domain here, which is the circle. What we're going to say is the following. We're going to say in order to cover this region, we want x squared plus z squared, we write it over here, we want x squared plus z squared to be equal to the radius squared. Now this will be the equation of any circle that is centered at the origin with radius r. But notice r, in order to cover this whole circle, we want r to go from 0 to 2. Because if r goes from 0 to 2, then we'll actually, well, the circles will actually cover all of this solid region here. But now as far as the angle goes, this is the radius, but as far as the angle goes, angle theta, theta must go in between 0 and 2 pi in polar coordinates in order for us to cover the whole region. From 0 to 2 pi covers the whole region. So the radius has to change from 0 to 2, and the angle must change from 0 to 2 pi, and we have this fact here. So what I can really say now is this double integral will turn into the following. So instead of keeping these integrals with these limits, we're now going to take the integral with respect to r from 0 to 2. Anytime I see x squared plus z squared, I can replace it with r squared. Notice the square root of r squared is just r. Here, this really is negative x squared plus z squared in parentheses, but that's r squared, so this really is 4 minus r squared. Okay. And that's dr. There's a little bit of a, not problem, but the thing is that when we're in polar coordinates over double integrals, we have to recall that dz dx is actually not replaced with dr d theta right away. It's replaced with r dr times d theta. And the reason why this r comes about has to do with the area. But again, if you haven't seen this before, I wouldn't really worry about it too much. Just kind of see the setup. I think really that's the most important part. Beyond that is just me using some different techniques to actually evaluate the integral now. So, but this r comes about because of polar coordinates and how you set up an integral over polar. And then for d theta, theta goes in between 0 and 2 pi, and that's it. So now, if we distribute this, well, this is r squared, notice. And if we distribute that r squared, we end up getting, let me move that way up here, let's say. It's a little too tall. There we go. We end up getting the integral from 0 to 2 pi of the integral from 0 to 2. If you distribute this r squared in, you get 4r squared minus r cubed. 4r squared minus r to the 4th. There we go. dr, then d theta. Okay. Now the antiderivative with respect to r is actually not that bad. That's going to be 4 over 3 r cubed minus 1 over 5 r to the 5th, evaluated between 0 and 2, then integral from 0 to 2 pi d theta. Now the fact that there's no theta inside of this expression here, I know that really this is just going to be multiplied by theta and then evaluated between 2 pi and 0. So really we're just going to multiply this expression multiplied by 2 pi really. Because it's going to be multiplied by pi, and pi is going to be evaluated between, it's going to be multiplied by theta when you take the antiderivative with respect to theta, because it's a constant. Then evaluate that theta between 2 pi and 0, you end up getting 2 pi times this expression minus 0 times this expression. But now this expression, finally, when you plug in 0 into any powers of the variable, you just get 0. When you plug in 2 cubed is 8 times 4 is 32 over 3, minus 2 to the 5th is 32 over 5. And if you pull 32 out, you get 64 pi times 1/3 minus 1/5. 1/3 minus 1/5, I went way off screen there. Let me scoot that over for a second. There we go. If we do 1/3 minus 1/5, that's actually going to be 5 minus 3 over 15, so that's 2 over 15. So 2 times 64 is going to be 128 pi over 15. So I know the last few minutes of this may or may not have been a little hard to follow, but at least the setup is has been shown, and the fact that you can set it up different ways depending on what type you're looking at. Now in this case, type 1 and I believe type 3 didn't really work, but type 2 worked. So that was good. And again, that's getting rid of y first, not z first. Awesome. So now finally, to end the video, we're going to take a look at a really awesome application of triple integrals. The last thing I want to talk about now is this property of triple integrals, but before we get there, let's discuss what was true for single and double integrals when the integrand is just the number 1 itself. So the integral of dx, double integral of dA, and so on. So the integral of dx of a to b, from a to b, is just the distance b minus a. So really this is the, I guess you can say, measure of a one-dimensional object. which is just length. Here, the double integral over a region D, dA, is just the area of that region. So this is the measure of a two-dimensional object, its area. Similarly, we now see this property that the triple integral over a region E in three-dimensional space of dV is just the volume of that region. So this is now volume now. Awesome. So now what we can do is we can use this idea to find volumes of certain things. And in fact, if you wanted to take the volume of, let's say, that shape we had from the previous example, it would actually be pretty similar to what we just did. So I'm not going to redo that nonsense again. I mean, it's not nonsense, but I'm not going to redo that again because it was a little involved, obviously. But here we'll find the volume of a tetrahedron. And let's try to graph this just so we can see what it looks like. Now remember, a tetrahedron is essentially a triangular based pyramid. It's a four-sided object where each side is a triangle. And now we have this plane, x plus 2y plus z is equal to 2. Remember how we graph this plane by finding the intercepts? So if we let two of them equal 0, one at a time, z would be 2. X would be, when these are 0, x would also be 2. And y, when x and z are 0, is, well, it's going to be 2y equals 2, so y is equal to 1 in that case. So what we end up getting is this guy right here. This is the plane. But now notice it's not as straightforward as you might imagine, because even though we have this plane, it's not actually, so the tetrahedron isn't just this. That would be if it was x equals 0, y equals 0, and z equals 0, but instead we have x is equal to 2y. Now x is equal to 2y, I would rather see this as y is equal to 1/2 x, because that's easier for me to visualize on the xy plane. There's a slope of 1/2, so you go up 1 over 2, and 0 is the y-intercept, so you end up getting this here, that. Now in this, let me see if I can see it here. Yeah, so on the xy plane, the way it looks is as follows. So if you go to this point where y is equal to 1 and x is equal to 2, you actually get the same point here, and we have this line like that. So this line is just a line on the xy plane, but in 3 space, it represents a plane that's parallel to the z-axis. So if we kind of imagine cutting this plane through here, let me try to make that look a little cleaner. So I'm extending this line that way, so we end up getting this plane cutting through there, and it goes up like that, crossing the z-axis. So we end up getting this shape actually. Okay. And then we have x is equal to 0, which is, well, the yz axis, and the z is equal to 0 is the xy axis, or the xy plane. So yz plane and xy plane. Okay, so again, this line kind of messes things up a bit, but it's still a tetrahedron. I'm going to try to draw that a little better though. In fact, let me try to shade it. So we end up getting this as being the floor part. We have this wall that goes from here to here basically. Let me try to do that in green or something. So that's what that looks like. That's still really hard to see. But yeah, it's not too bad. I mean, it's still a tetrahedron. It looks more like this. So we have that guy, we have this straight line like this, we have a line like that, this line coming up, and that line there, and this line here. So it's just basically a cut of the tetrahedron we saw before we considered this line x equals 2y. But anyways, visualize it however you like by kind of drawing it. The more you draw it on your own, the more you'll be able to see what it actually looks like. But yeah, it's just a tetrahedron. Now as far as how do we find the volume of this thing, what we're going to do actually is we're going to try to write this as a type 1, type 2, or type 3 region. I'll try to do type 1, and then we'll just take the integral, triple integral of dv. So let's see if we can do that now. So let's see, so E is going to be the triple, order triple xyz, such that x is going to be in between, well I guess we could say this, xy is in some domain D, where z is in between what? So z, lowest can be 0, and highest can be on this plane. So if you solve for z here, you just get 2 minus x minus 2y. And in fact, these will be the limits for z. Now the limits for y and limits for x we can work out on our own by looking at what d is and looking at the xy projection. So we could do that, but I think best thing to do is just to jump right into the triple integral. So for the first limits, we'll have 0 to 2 minus x minus 2y. Okay, that's going to be, remember, we're taking the integral of just 1 basically, dv. So this is going to be with respect to z, so dz first. And now if you look at the projection, let me draw the projection here on the xy plane, since we lose the z dimension now because we integrated with respect to z, we end up just getting this piece here. So we have, again, this line that connects from, it looks like y equals 1 to x equals 2. And then we have this line here that cuts through, which is the line x equals 2y, which we discussed earlier, which looks like that. So yeah, it's a little weird, but yeah, what we end up getting really is this. So this ends up being the floor projection, if the floor is the xy plane, of this region here, of the tetrahedron. So now what we can say is, we can say x is going to be in between 0 and 2. Notice it indeed crosses through 0 equals 2, or x equals 2. And this point looks to be like the point 1 comma 1/2, just from symmetry. I mean, we can tell because we know what these lines are. Oh, and you know what? What's really nice about this is, maybe it's actually not nice, but what this ends up being actually is a type 2 region, not a type 1 region, because on top we have 2 functions, not just 1. So we could split it up into 2, but and it's best actually to view this as a type 2. So instead of x being in between 0 and 2, we're going to say x is bounded by this top curve and this bottom curve. If you tilt your head and imagine this one being on top and this one being on the bottom. But then y would then go from 0 to 1/2. Now, just to ensure that these values 1 and 1/2 are indeed correct, what are the actual equations of these lines? So we know the equation of this line we've already established is just x equals 2y. Now this line comes from the plane, but notice on the xy axis, the z is equal to 0. So for this plane, if z is 0, then we get x plus 2y equals 2 for this line. Perfect. So now again, just to show that that is indeed correct, if you actually convert this to slope-intercept form, you would subtract x and divide everything by 2, you get negative 1/2 x plus 1. So we have a y-intercept of 1, which is indeed the case, and then we go down 1 over 2 because the slope's negative 1/2, perfect. And can we show that these two actually intersect at 1 comma 1/2? Plug in 1 into each of these. Well, plug in x equals 1 to each of them. When x is equal to 1, y has to be 1/2 here, in order for 2 times 1/2 to be 1. If you plug in 1 here, you get negative 1/2 plus 1, which is indeed 1/2. Perfect. So as far as the type 2 region goes, the y values are going to be in between 0 and 1/2. And I always want the constant limits to be last, so that's how I know to put that in the last integral. And now the intermediate limits then will be the actual bounds of x. So x is going to be largest, this. So instead of solving for y, really we should solve for x. That's easy though, just subtract 2y. So we'll get 2 minus 2y for the upper limits. 2 minus 2y, let me squeeze it in there, there we go. And then for our lower limit now, we're going to just have x is equal to 2y itself. Perfect. Yeah, so it's a lot to set up, but like I mentioned previously, the setup is the hardest part with these, usually. So now, antiderivative of 1 with respect to z is just z itself, but if you evaluate z between 0 and, so let me just write, z evaluated in between 0 and 2 minus x minus 2y is just equal to this itself. So really we have this double integral of 2 minus x minus 2y, dz is gone, now we have dx and dy still, let me border this off a bit, and now we have the limits 2y to 2 minus 2y, and then 0 to 1/2. Now again, I've lost space here, so I'm going to erase for space, shift this up, and continue. Right, there we go. So now let's continue where we left off on. Now the antiderivative of this with respect to x, 2 has antiderivative of 2x, and 2y has antiderivative of 2yx because they're constants. Antiderivative of x itself, though, is negative 1/2 x squared. So we have a 2x in front and now a negative 2xy behind. Evaluate this guy between our limits 2y and 2 minus 2y. Yikes. Now again, we're plugging in, we're plugging these into x, that is. So we're going to have, there's a lot to actually plug in. But that's okay. Let's just do it as is. So we get 2 times 2 minus 2y minus 1/2 times 2 minus 2y squared minus 2 times 2 minus 2y, times y minus, so that's the first guy. And now plugging in 2y everywhere we see an x. So it's 2 times 2y minus 1/2 times 2y squared minus 2 times 2y times y. Okay. Hopefully a lot of this collapses, but let's see. If you distribute the 2 here, we get 4 minus 4y. Minus, you have to square this out, then distribute the 1/2. I guess I'm okay with that. I'd rather pull the 2 out first, but it's in a square. So if we pull the 2 out, we're going to have to square the 2. It'll become 4, but 4 over 2 is just 2. So really, if we pull out the 2, you have 1 minus y all squared. And this is actually okay to expand. If you expand this out, you just get 1 minus 2y plus y squared. If you distribute the negative 2 into this, which I'll do right now, you get negative 2 plus 4y minus 2y squared. So hope that part wasn't too bad. And now here I'm going to distribute y and the negative 2 at the same time. So the negative 2 part will make this negative 4 and then positive 4. But the y part will make this have a y and make this have a y squared. Okay. And now here we're going to get 4y. Here we're going to get, let's see, that's going to be a 2y quantity squared is 4y squared times 1/2 is 2y squared, so it's negative 2y squared. And then we have minus 4y squared finally. Now, this is all being subtracted, so I'll actually distribute the negative simultaneously. I know I'm doing a lot here at once, but I hope it's not too much that we can actually handle following. I think it should be okay. Right, so does anything combine? Yeah, definitely. 4y's cancel here. These 4y's seem to combine. And then we have these y squares canceling and these y squares combining. And these actually combine as well. That's a lot to look at. But right, so what we have left over now is just 2. And then we have minus 8y plus 8y squared, it looks like. Okay, so I think that's not too bad. I mean, there's a lot. So try to follow that on your own to see if you get that indeed. So now this part is taken care of. Now we have this x integral just collapsing into this expression here. So with that being said, let me erase this now. A lot of erasing as we go along, which isn't recommended, but provided it's correct. We now have the integral from 0 to 1/2 of this expression. And in fact, we can pull the 2 out if we like. I don't know how useful that'll be. We'll just keep it like this, that's fine. Now we have dy. Perfect. Now the antiderivative with respect to y will just be 2y minus 8 over 2, which is 4, y squared, plus 8 over 3, y cubed. Evaluate between 0 and 1/2. When you plug in 0, they're all just powers of y, so you just get 0. So now let's erase all of this work now and continue this evaluation. When you plug in 1/2 in for y, you get 2 times 1/2, which is 1, minus 1/2 squared is 1/4, times 4 is also 1, plus 8 over 3 times 1/2 to the third. 1/2 to the third is 1 over 8. So these cancel, we're just left with 1/3 now. So the volume of that tetrahedron is just 1/3. Wow. So I hope that was a really nice way to finish this this video. I think it was fantastic. I hope you enjoyed it as well. I'll see you in the next videos. We'll keep running through Calculus 3 and seeing a lot more really fun stuff. Hope you enjoyed this. Thanks for watching. I'll see you in the next videos. And I think that's all I need to say. See you then.